As a continuation of our AVL tree lecture, we shall now look at the implementation of the insertion method. Then after that, we look at the deletion, discuss it, how to do it manually, understand it conceptually, and then we shall also look at its implementation as a Java code. So now before we look at the insert method itself, as we shall see in the AVL tree class, which we will discuss as part of the lab, we have made a slight changes in our node class as compared to the BST node. So the AVL node is very much similar to the BST node. However, because we're going to be computing, we're going to be needing the height very much. Virtually after each insertion, we have to find the balance factor, and finding the balance factor require computing the height. So instead of calling the height method as we did in BST to keep recalculating the height, this time we decided to define the height as an additional variable in the node object, so that to get the height we just access that variable. So this is one of the main difference between a BST node and AVL node. So in addition to key, left and right, now we have a new variable int height. So basically this will tell us what is the height of the tree rooted at the current node. Okay. The other change, of course, we have made is the constructors now must initialize, in addition to the other variables, they must initialize the height. So looking at the main constructor, which receives the element left and right, in addition to setting key left and right with the received arguments, now we have to compute height. So height of the current node, which is being created, will be the maximum of left.height and right.height plus 1. So find which of the left or right subtree is the tallest, get the height, and then add 1, and that will be the height of the current node. Right, so this is if we receive left and right subtrees. What if we receive only the info, so only the key? If we receive only the key, the node we're going to create is a leaf node, and obviously the height of a leaf node is 1. So in that case we just say height is equal to 1. Okay. And this constructor, remember, it will create an empty tree. So an empty tree will have no node, so height will be 0. So that is the change we have to make to the node class, so that we don't have to keep calculating the height every time as in BST, because in BST we don't have height as a variable, but we have a method to use to get it. Type. Now, because of this, we have changed the height method. Now it's much simpler. It simply returns p.height, because we have height as a variable in the node. So if we receive a node p, to return its height, just say return p.height. Of course, you have to check that p is not null. If it is null, return 0. Okay. So this is one change we have to make to the AVL tree class. Okay. The next set of method we're gonna look at before we start looking at the insertion method itself are the rotation methods. So let us look at a method here called rotate left. This is supposed to help us rotate a tree rooted at P to the left. So it's very simple. Basically, three main lines to execute, actually four, and we will have done the left rotation. But to make it clearer, I have here a scenario where P is referencing to our node X. So we need to rotate node X to the left. So we shall be following each of this line against what will happen to this tree. And let us see if it will really rotate X to the left. Okay, so the first thing done is we define a variable parent and we initialize it to p.right. Remember, when we rotate left, the parent will become the current right child. So define a variable parent to point to the right of p. So our parent will be pointing to y. Okay. Next is change p.right. Let it becomes parent.left. Okay, p.right. Let it becomes parent.left. Remember, when we rotate x to the left and y goes up to become the new parent, x will be the new left of y. So what happened? The current left of y, it becomes the right of x. So it is because of that we are saying p.right becomes parent.left. This is the current p.right. We want to kill it and let it point to parent.right.left. This is parent.left. So this is what will happen. Okay. Next, parent.left, change it to becomes p, because again, when we rotate y to the left, y will become the new parent, and p will be to its right. Therefore, parent.left becomes p, like this. Parent.left becomes p. Okay, parent.left becomes p. So this is basically what you need to do. If you notice now, well, before we move on, we need to, of course, update the height of both P and parent, because they're going to change in height. Whereas the parent will move up, P will go down. And since we are saving height as a variable in the node, we have to adjust it to correct the value according to the new state. So p.height will becomes the maximum of the height of p.left. This is p.left. So find the maximum of that, and the height of p.right. The new okay, this is p.right. Okay, so find that and update the height of p to be that. Similarly, the height of the parent has to be changed. Parent.height becomes 1 plus the maximum of parent.left. Notice that P is now actually the parent.left. So the height of this and the present height of right, the height of the present right, take the maximum and add 1, and that will give you the height of the parent. So once you do that, this is what you will end up with. Okay, you see y has gone up. Okay, it's left is now x. Okay, and x has been right now as t3. This is what left rotation will do. And at the end, we're going to return parents. So return parents. Okay, so parent is our updated tree after doing the rotation. This is basically what left rotation will do. As you can imagine, right rotation will do very similar. I don't have to go and explain it in detail. Basically, just change any occurrence of right here with left, and you will have a right rotation. It's doing exactly similar thing. The other two rotations, where is left, right? Okay, it seems I missed the double left right rotation. We shall discuss it when we look at the code. But basically, it's nothing but doing left rotation and then followed by right rotation, or vice versa. We shall see it when we come to the code. So having discussed the rotations, now let us look at the insert method. How do we implement it? As the algorithm says, insert using BST procedure, and then check if the tree is unbalanced, you balance it. So this method actually is very similar to the insert method of BST. As you recall, when we reach null, we are ready to do the insertion. Otherwise, we keep going left or right. The only difference now is if after inserting the element to the left, we have to restore balance. So this if statement is the one that is trying to restore balance. Okay, how is it doing it? First, it checks if the difference in height, because in this case, if you notice, we have done the insertion on the left. So it is the left we expect to be taller, having added a new element in it. So subtract from the expected higher, which is the height of the left, minus the height of the right. So what is the balance? If you get 2, it means the tree is no longer an AVL tree. So we have to balance it. Okay? Now, getting 2 is not enough for us to know what to do. We have to now check, what about the left child of this node? Okay, because we have done insertion on the left, but what about the balance factor of the left of that? If the balance factor is negative, then it means actually what we have done is a left-left. So what we will do is single right rotation. So you see we're saying P becomes rotate right P. Okay. On the other hand, if balance factor is 0 or greater than 0, so actually the element was inserted on the right of the left. So it was left right, and therefore you will call the rotate left right method to restore the balance. Okay, what if the insertion was done on the right? So the key that you are inserting turned out to be greater than P dot key, so you inserted on the right. Okay, and you have checked the balance between the height of the right and that of the left is now 2. Okay, so it is outside the expected range. So still we don't know yet what to do. We know it's somewhere to the right, but is it right or is it right left? To check, we have to now check the balance. How does the element we inserted, how does it compare to P.right.key? Okay, if the element was greater than P.right.key, it means we have inserted right. Therefore, our rotation is to do is rotate left. Otherwise, it was right left. So we have to do right left double rotation. Okay, so this is the addition we have to make to the insert method of BST for us to achieve the insert method of AVL. The final thing we have to do in this method after doing the rotation is to adjust the height of P.height. So the new P.height becomes Again, the maximum of the height of the left and the height of p dot right plus 1. Okay, so once you do that, now you can return p. So these are the only changes needed to improve our insertions method so that it guarantees balance. If you are asked to compare between the insert method of AVL and insert of BST, which one do you think is more efficient in terms of time? Obviously, the insertion of BST is faster because we don't have to do any rebalancing. Okay, so similarly for the deletion, the deletion of BST is faster because no rotation is involved. But these are the costs you have to pay to make your searching faster. So the searching in AVL is much faster than BST because AVL is always balanced. So this is a typical situation that we have in data structure. You never get something for free. We have achieved a very fast searching, but at the cost of less efficient searching, insertion and deletion. Yeah, and this is just by the way. As usual, of course, each of these recursive method, they come with an auxiliary method because we have to give an initial value for p. So the initial value for p is root. Okay, so that brings us to the end of insertion. Now we're going to start about deletion. How do we delete from an AVL tree? It's very similar to insertion. Delete using BST deletion by copying algorithm. But after that, you have to check if your tree becomes unbalanced. In that case, rebalance the tree before you proceed. So again, like insertion, if you are deleting a number of keys, after each deletion, you have to balance the tree before we move to the next deletion. Okay. Now there's a slight difference in terms of finding the problem, the type of unbalance in case of deletion. In the case of insertion, it is very easy. Just move from the node that you have that has problem towards the new node and count twice how you are moving, left, right, or right, left, or left, left, or right, right. In this case, we have not inserted any node. We have in fact deleted a node. So the question is, how do we find the type of problem? Yeah. So this is, we have to come up with another strategy here. As I will show you in an algorithm in a moment, there's a small algorithm you can use to know what type of deletion problem it is. But before that, two important points. The first one is, in case of deletion, you have to check for imbalance and do the rebalancing starting from the node that has, from the immediate parent of the node that you have just deleted, all the way to the parent, going up all the way to the root. Okay, it said the checking for imbalance and rebalancing must be done for each node along the path from the parent of the deleted node until the root. So you have to repeat the process from the parent of the deleted node. Is it balanced? If not balanced, you rebalance it. Then go to the parent of that. Is it balanced? If not balanced, you balance it. You keep doing that until you reach the root. Okay, this is one issue we have to know. The second one is, for each ancestor P of the delete node, we must check and rebalance the tree according to the following algorithm. Yeah, this algorithm actually gives you a way to find what type of deletion you should do. Is it left, left, right, 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 left, and so on. This is the algorithm. So first of all, you have to check the balance factor of your P. Okay, the P where you have just done the parent of the node that you have just deleted. Okay, from that actually upward, you have to keep repeating this, as we said in this point. The checking and rebalancing has to be done from the immediate parent until the root. So when we come to a particular node, this is the algorithm we follow. First of all, we check the balance factor of the current parent. Is it -1? Meaning, is it less than -1? Meaning, is it -2? If it is -2, then we have 3 cases for having -2. Okay, it could be -2 and the left child is -1. It could be -2 and the left child is 0. And it could be -2 and the right child is 1. Okay, so we have to check further before we know what to do. Just knowing that the parent is having -2 doesn't yet tell us what to do. We have to check the balance factor of its left child. So that's why here there's another if statement that says if the balance factor of P dot left, if it is less than or equal to 0, so if it is one of these 2 cases, then we just need to do a single right rotation. Okay, because actually it is a left, left. Okay, so just a single right rotation will solve the problem. That's why you see here, P becomes rotate right, P. Otherwise, if it is not less than or equal to me, it is greater. Okay, so it is 1. If that is the case, then we have to do a double left right rotation. Okay, so rotate left right. Yeah, so although we don't have a new node to use to know what rotation to do, we can still know what to do by computing the balance factor. First, compute the balance factor of your P. If it is -2, then find the balance factor of its left. If it is less than or equal to 0, then you only need to do a single right rotation. But if it is 1, okay, then you have to do a double rotation. On the other hand, if the balance factor is greater than 1, meaning it is 2, then again you could have any of these 3 cases. So each of these 3 cases is +2. So what to do? You again have to compute the balance factor of the right child this time, not the left. Okay, the balance factor could be 1, could be 0, or could be -1. If the balance factor of the right child is greater or equal to 0, then we only need to do a single left rotation. Because as you can see, this is right, right. So just rotate left. Otherwise, it is -1. So in that case, you have to do a double right left rotation. So this is basically the algorithm that we will follow in determining what to do. And as we said, we have to repeat this from the immediate parent of the deleted node all the way to the root node. We will take some examples, and after that we will look at the actual full code of the deletion method. Okay, now there are 3 deletion cases. Like we saw, there were 3 insertion cases. Similarly for the deletion. Deletion that doesn't cause an imbalance. Deletion that requires a single rotation. And deletion that will require 2 or more rotations. Let's take the first case. Deletion that doesn't require any balancing. So suppose in this tree, which is currently balanced, it is AVL, Suppose you want to delete 14. 14 is here. Obviously, deleting it, as we said, after deleting it, we have to check all the ancestors of the deleted node, from the immediate parent all the way to the root. So we have to check, is 15 balanced after the deletion? If find, is 13 balanced? If we find any of them not balanced, we have to balance it before we move on to take the next one. So in this case, this is the result you're going to get after deleting 14. The balance factor of 15 has changed to +1, and the balance factor of 13 has remained actually -1. No change. So you will ask yourself, is 15 balanced? Of course it is. So nothing to do. But you don't stop there. You ask yourself, is 13 balanced? Again, it is balanced. So in this case, there is nothing to do. This is the easiest case. Deletion that doesn't cause an imbalance. Okay, let's take case number 2. Suppose we want to delete 40 from the following tree. Okay, delete 40. Again, after deleting 40, you have to check all the ancestors of 40, meaning 35 and 30, one by one. All right. So, if you delete 40, this is what you have. The balance factor of 35 has changed to -2. Okay, no change yet in the balance factor of 30. It is still +1. But we have to check it again after balancing 35. All right. So, obviously 35 is not balanced, and the balance factor is -2. Do we know what to do? Not yet. If it is -2, you have to check the balance factor of the left child. The balance factor of the left child turns out to be -1. If it is -1 or 0, all you have to do is single right. So we're going to rotate 2 to the right. If you do that, 32 will move up to become the new parent of 35. 35 will go down to become its right child. So this is what you end up with. Okay, so after this, you still have to check what is the balance factor of 30. Luckily for us, the balance factor of 30 is now even better. It was +1 before, now it is 0. So we are done. Okay, let's take another example. Consider this AVL tree. Suppose we want to delete 32. So 32 is here. Okay, deleting it, we have to check all its ancestors, 17 and then 40. To check if they are not unbalanced, we have to balance. Yeah. So deleting 32 will give us this tree. Obviously 17 is now a leaf node, so its balance factor is 0. So nothing to do for 17. But 44 has a problem. It is now +2. Okay, so +2 is a problem. Next is, if you have +2, you have to check the balance factor of the right child and see what is it. If it is 1 or 0, you only need to do a single left rotation. In this case, it is 0. So we only need to do a single left rotation. If you rotate to the left, 62 will move up to become the new root. 44 will go down to become its left. The current left of 62 will be the right of 44. Okay, so this is what you will end up with. You can see 62 is your new root. 44 is its new left child. The former left child of 62, which is 50, is now the right of 44. This is single right rotation. Okay, so this is how to do deletion in this case. Let's see case 2. All the previous cases have been just one rotation needed, but in this case you have to do more than one. Okay, suppose you have this tree and you need to delete 40. Okay, so this is 40. Deleting 40, again, remember you have to check all the ancestors of 40, which are 35 and then 30. Okay, so this is the result you get after deleting 40. The balance factor of 35 has changed to -2. Okay, what to do? We have to check the balance factor of the left child. It is -1. Therefore, we only need to do a single rotation of a single right rotation of 35. So 32 will come up, okay, to replace the 35. 35 will go down to be its right child. Well, it doesn't have any right child now, so there's nothing nothing else to do. So this is what you have. Okay, as you can see, 32 has gone up, 35 has moved to its right. But notice now, after doing that, the balance factor of 30 has changed. It was -1 before, now it is -2. So this is why it's not enough to just balance the parent. You have to repeat the process until the root. So now we check 30. It is -2. All right. So how do we know what to do? We have to check the balance factor of the left child. If it is -1 or 0, we only need to do a single right rotation. It is -1, so just a right rotation about 30, meaning 20 will move up to become the new root. 30 will go down to become the right child of 20, the new right child, that is. The current right child, which is 25, will be the left child of 30. So this is what you have as the final answer. You can see 20 is the new root. Okay. To its left, 30 has gone down, and to the right of 30 we have 25. Okay, so this is the final example that we have on deletion. Finally, we look at the implementation of the algorithm, as we shall see in the full Java code when we discuss the lab. This is the deletion method. It basically involves 3 steps. The first step is exactly as in BST. Delete based on deletion by copying. So all of this is deletion by copying. If you compare it with the delete method in BST, it's exactly the same. You keep going left or right until you find the key. When you find the key, you check, is it one of the 2 trivial cases? If it is, you solve. Otherwise, you have to find the successor, which is the minimum from the right, replace it, and then do the delete the successor. So this is deletion by copying, exactly as we discussed. Now, after that, you have to compute the height of P, the new height of P, having done the deletion. Okay, so that is step number 2. P dot height becomes the maximum of the height of P dot left and height of P dot right plus 1. Now, based on this P dot height, we will have to decide if there is a need for rotation to balance the tree or not. That is step number 3. And this is it. Exactly as we saw in the algorithm for deletion. Actually, the code here was copied and pasted there. Rebalancing the tree. So having updated the height of your P, now what is its balance factor? If the balance factor is -2, less than -1 means -2, then check the balance factor of the left. If it is less than or equal to 0, you rotate to the right. Otherwise, you rotate to you do a double left-right rotation. Okay. Otherwise, if it is not less than -1, is it greater than 1? meaning it is 2. If it is 2, get the balance factor of p dot right. Okay, if the p dot right is greater or equal to 0, meaning it is 1 or 0, then you only have to do a single left rotation. Otherwise, you do a double right-left rotation. Okay, at the end you return. So this is basically the addition you have to add to the deletion of binary search. In addition to deletion, now you have to update the height, and based on the height, compute the balance factor. If it is either -2 or +2, then you have to rebalance the tree accordingly. That brings us to the end of AVL tree, and we will stop this lecture now. Thank you very much.